When it comes to substitution, we do have a nucleophile coming into attack an electrophilic position, but there's a bit of a problem. We can't just go ahead and add another atom or another group without breaking the octet rule, so something has to leave. And there are two ways we can do this. We can either come in with all full force and force the other atom to leave, or another atom, or we can simply nicely let another group leave and then come in to take its place. You should know that this first forceful way of doing things, a concerted way, is the Sn2 mechanism. So let's look at what we have here. I have a sodium ethoxide, so we'd expect our ethoxide to be our nucleophile. We have that electron density on the oxygen, which should here be represented by a lone pair. We'll have that come in and attack an electrophilic position, which will force electrons up onto this bromine, causing it to leave as a leaving group. Now, one thing to consider here is the position that we're attacking. Since this stronger nucleophile, this ethoxide, is coming in to force the leaving group to leave, it's having to actually reach the electrophilic site. And since we have a tetrahedral arrangement of atoms around this carbon, this electrophilic site, it has to be able to fit through. But here, as you recognize, it's a primary alkyl halide. The only two other atoms here are hydrogens, pretty much the smallest options we could get. And I know it's hard to see that other one. So here, we really have no problems getting in the way of a Sn2 mechanism. We have not too much steric hindrance. And those are just the things you keep in mind as you're working through these problems. So then we would expect to draw our product. We had the ethoxide coming to take its place. And I'll go ahead and write the bromine here, which left as a leaving group, and it's relatively stable. And being a larger atom that is electronegative, it can stabilize the negative charge. We're going to apply the Sn2 mechanism again, and this problem is going to draw out a few more concepts that we can apply. So let's say we'll work with a sulfur nucleophile this time. Have my negative charge. So we have our nucleophile here, and based on the molecule above, we'd expect that, okay, we'd be attacking here. Before we go on, there are a few things you want to consider. Compared to the last problem, we're actually dealing with a secondary substrate, or a secondary carbon, since it's connected to two other carbons. Now, since there's more space and more steric hindrance around this position, it's not going to be as effective for Sn2, but we're going to go ahead and go anyway, and we'll learn later in this section how we can actually facilitate Sn2 mechanisms. But another thing to consider is what our leaving group will be. If this OH group were to leave, this hydroxy group, we would get a negatively charged, or just a hydroxide. And this is not as stable of a leaving group as what we would want. So this isn't, since the leaving group is what we would call a bad leaving group, we need to do something before we can actually successfully approach an Sn2 mechanism. Rather than do the attack now, what we can do is actually convert this OH group into a good leaving group. And the way we can do that is something called tosyl chloride and pyrimidine. And it's hard to read the handwriting there, excuse me. But what this does is, when I write out the molecule again, it transforms the OH into tosylate, which is usually written as OTS. I'm trying to make the T clear here. But when we look at the structure of tosylate, has resonance stabilization, and therefore it's a much better leaving group since we're spreading this negative charge over a larger space. Now notice here that the stereochemistry didn't change, we just changed the functional group. So now I'll rewrite my nucleophile again, the sulfur nucleophile. We'll once again have the attack as we'd expect, and we're having the leaving group leave. We're having this concerted motion. So when I write that, our product would be, get that carbon skeleton down, we have that. But what about the stereochemistry? Well, you should know that we'd expect an inversion of stereochemistry. So instead of a wedge, we'll get a dash. One way to think of this is that through this backside attack, it's almost as if the nucleophile is the wind and the electrophile is an umbrella. So you think of a strong storm where, let's say I had an umbrella. Do my best to draw a good umbrella here. That's actually pretty good. And I have a strong wind come in and attack. So our electrophilic position is probably the point or the vertex of the umbrella. Well, with this strong wind that comes into it, this attack, what happens is the attack was so strong that I'm actually getting an inversion of the stereochemistry, or these points, because the wind was so strong that it turned the umbrella inside out. That's the same idea we're working with here. Once the wind comes in and attacks, or the nucleophile comes in and attacks, then it's changing the 3D configuration of the substituents. So I could say, if I wanted to elaborate on the metaphor, I had maybe a chlorine here, something else. Of course, this isn't the most exact representation. And then I guess that would be here and here. But you can see that through this backside attack, it's actually forcing the molecules kind of to flip over, to invert themselves, and thus we get stereospecific inversion when it comes to Sn2 mechanisms.